Watching the sunrise is an inspiring experience as light paints the sky with beautiful colors. But what about light gives it this beauty? Let's look at the light through the eyes of a chemist. This is Real Chem. One of the most challenging aspects of learning modern science is that it involves phenomena that we do not directly experience in our everyday lives. So we must expand our intuition. The matter around us seems continuous, but it is actually composed of small particles we call atoms and molecules. Light is similar. It appears to be a continuous wave, but is composed of particles we call photons. Let's explore. Many of the things we experience about light can be understood based on the wave character of light. The beautiful oranges and reds we see in a sunset are due to scattering and refraction behaviors that are common to wave phenomena. And this wave characteristic applies to radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. Radio waves are like deep bass notes. They have low frequency. Gamma rays are like high-pitched treble noises. They have high frequency. Visible light is a narrow portion of the full electromagnetic spectrum that our eyes have evolved to detect. But that's about us, not the radiation itself. From the radiation's perspective, the only difference between the infrared radiation, or IR, of a heat lamp used to warm food and the ultraviolet radiation, or UV, of a lamp used to sterilize medical equipment is the frequency of the light. Now, both lamps may be putting out the same amount of energy, but IR will warm your skin, while UV may damage it. But why is that? Well, to answer this, we need to consider the particulate nature of light. Light is also composed of photons. The energy of each photon is proportional to the frequency of the light, where the proportionality constant is called the Planck constant, or H. UV light has a frequency that is 10,000 times larger than IR light. So each UV photon has 10,000 times more energy than an IR photon. For each high-energy photon emitted by the UV lamp, the IR lamp is emitting 10,000 low-energy photons. It's also important to know that matter typically interacts with photons one by one, with plenty of time between to spread the energy out as heat. It's like under the UV lamp, my hand is getting hit with one bowling ball each minute, potentially breaking my bones. While under the IR lamp, my hand is getting hit with 10,000 foam balls each minute, giving me a gentle massage. For the molecules in my hand, it is somewhat similar. The UV photons have enough energy to break chemical bonds, while the IR photons just warm the molecules and do not change their chemical structure. Light has both a wave-like and particle-like character. This is often referred to as the wave-particle duality of light. But it is helpful to know that these characteristics coexist and are not in conflict. It all depends on what we are trying to understand about light. To understand the colors of the sunset, we can get pretty far considering only the wave nature of light. But when we think about the interaction of light with matter, we often need to consider the particulate nature of light. That light is composed of photons, and that UV photons pack a much bigger punch than IR photons. So explore and remember to have fun.